Let us discuss the electric field due to a disk. So I have a disk. Disk is having r radius. Total charge on the disk is basically q. And I have to find electric field at this point P, which is lying at a distance x from the center of the disk. What I am going to do is, first the surface charge density in the disk. Charge is distributed over an area. So what is that? Sigma is surface charge density, that is total charge q divided by total area, which is pi r square. Now what I am going to do is, I am going at a random small r distance and I am going to take a ring of width dr. And now due to that ring, I am going to write electric field over here and then I am going to integrate it. So to write that, let us say charge on that ring is dq. How do we write dq? So here charge is distributed over an area. So dq is nothing but charge per unit area times the area of the ring, which is nothing but 2 pi r dr. See, when you expand this ring, the length is 2 pi r and the width is dr. So it is like a rectangle having a length as 2 pi r and width as dr. So that gives me q by pi r square times 2 pi r dr. That is pi is gone. 2q by r square r dr. This is my dq. And now let us write small field due to this ring. So small field due to this ring is given by k. What was the formula for the ring? The formula was kqx divided by x square plus r square raised to power 3 by 2. Now I am writing k is k. The charge on the ring is dq. So dq is what? 2q by r square r dr. This is my q. X. What was x? X was the distance from the center of the ring, which is still x. Divide by r square plus x square. What is r? R was the radius of the ring. But here the ring has smaller radius. So we will say x square plus small r square raised to power 3 by 2. And now I am going to integrate this to get the total electric field due to the disk. So let us integrate it. What will be the limit? Here r is changing. So limit on r is nothing but limit on r is 0 to capital R. I will cover the entire, like such small rings will cover. So it will form the entire disk. Now let us integrate. So this gives me k is a constant which will come out. 2q is a constant. R square is a constant. And here our small r is a variable. This x is also constant, so will come out. And this is 1 r dr divided by x square plus r square. Remember, this x is not a variable. X is this distance. Whether you take this ring or you take a bigger ring, this distance is always x. So this x is a constant. And now integration of that from 0 to r. For this I am using substitution. How do we use substitution? For substitution I am saying, let us say x square plus r square is equal to t square. Differentiate both sides, you get that x is a constant. Differentiation of any constant term is 0. So 0 plus 2r dr is equal to 2t dt. So I will say r dr is nothing but t dt. So this becomes t dt. Integration of t dt. And what about this raised to power 3 by 2? So this is t squared. So the 2 is gone. So this becomes t cube. 1 t is gone and this becomes 1 by t square dt. And integration of that thing is going to be nothing but minus 1 by t. And what is our t? T is root over x square plus r square. So integration is 1 by minus 1 by root over x square plus r square. So this is the integration. So I am going to integrate it. So I'll just put that directly over here and then substitute the limits. So integration is k 2qx by capital R square minus 1 by root over r square plus x square. What is the first? First is capital R square plus x square minus plus 1 by root over x square plus 0 square, that is simply x. And this is going to be my answer. So let us try to simplify our answer and make it a proper formula to remember. So now this x goes inside. So this x is going inside. and this is x. So this x by x is 1. What about x by r is root over r square plus x square. This is x and this length is root over x square plus r square. So this is like base upon hypotenuse. If this angle is theta, then this thing is nothing but cos theta. So I'll say this is 1 minus cos theta. And what about this? 2kq by r square. So 2k is 1 upon 4 pi epsilon naught. And the charge divided by r square. So here pi r square is charge upon area. So this thing is sigma. And this 2 gets cancelled. So we get sigma by 2 epsilon naught. So this entire thing is sigma by 2 epsilon naught. So the formula which we get is sigma by 2 epsilon naught. In bracket, we have 1 minus cos theta. And this is the formula for the electric field due to a charged disk, uniformly charged disk. So finally, this is the formula which you need to remember. It is sigma by 2 epsilon naught 1 minus cos theta. And what is cos theta? Cos theta is nothing but this length divided by this length. If you want, you can resubstitute it. So this is the formula which you need to remember. Now let us discuss electric field due to a spherical shell. Now that shell might be a conductor or it might be an non-conductor. So this is just a shell, the boundary and charge q is lying over this shell. So this charge is lying over an area. So there are two cases which we are going to discuss. One is electric field for a point which is lying inside, and that is at a distance r which is less than the radius. And next case which we are going to discuss is the electric field point at a distance r which is greater or equal to r. Means this point is either on the surface or outside. To be precise, we'll be calling it outside, but that is valid for surface as well. So these two cases we are going to discuss. So this we are going to call it as E in, and this we are going to call electric field outside the shell. So let us discuss them one by one. First, for a point which is inside. So let us say I have to find electric field at a distance r at this point, and I am calling it Q. So I needed to find electric field at Q. So what I am going to do is I am going to take a Gaussian surface. This Gaussian surface is also a spherical surface which is having a radius same as our distance r. Okay, and then this is the radius capital R. So this is the r, and we needed to find the electric field over here. So I will say that this is my Gaussian surface, and with symmetry, suppose there is any electric field which is outside, then due to symmetry, if this is over here, then electric field must be here. Here also electric field like be radially out, right? So let us see in value, the magnitude of electric field is E, and let us call that E in. So what will be the flux? What does Gauss law says? Gauss law says that total flux is equal to Q in by epsilon naught. How do we write total flux? Total flux is basically integration of E dot ds, and here the area vector on this assumed spherical Gaussian surface. So this is a spherical surface and area is radially out. So area is also out and E is also out. So the angle between any small area vector and the E vector is going to be basically 0 degrees. So E into small area into cos 0. And when you integrate it along the surface, basically it gives you E into area. Like it is E is a constant, like due to symmetry we can say all E will be same. And then integration of dA, cos 0 is 1, and integration of dA is nothing but total area, so which is nothing but 4 pi small r square. So this is the total flux is equal to Q in. What is charge which is lying inside this Gaussian surface? If we see over here, charge is lying on this surface, not inside the Gaussian surface. So eventually we will say that here in this case the Q in, this part is 0 and the 0 upon epsilon naught. So here this is a E has to be 0. So E comes to be 0. So electric field inside a spherical shell at any point, given that this R is less than radius, then with Gaussian law we can say the charge inside the spherical Gaussian surface is going to be 0, and due to that our electric field will be 0. So we will be saying that electric field inside a spherical shell, whether conductor or non-conductor, is going to be 0 only. Now next case is that we are going to talk about R is greater or equal to R. So let us consider this point P, and here I am assuming again the Gaussian surface. It is same as the previous case. Only thing is here the total flux again is Q in by epsilon naught. So here also I am assuming like E. Let E be the magnitude of electric field and the direction be radially away. Why we are saying radially away? Because I am assuming this to be positively charged. So this total charge is Q and the E is basically radially away, right? So the flux is going to be again same, the electric field into total area. So cos theta is going to be cos 0, which is 1. So E into total area is 4 pi r square. What about Q in? Q in is nothing but total charge Q, because entire charge Q is lying inside our Gaussian surface divided by epsilon naught. Let us just rearrange it. So E comes to be, this 4 pi square goes here. So Q by epsilon naught and 4 pi r square, I am writing it over here. So what is this? This is like 1 by 4 pi epsilon naught into Q by r square. So this is nothing but KQ by r square. And this formula is familiar. This formula is same as if there is a point charge. Let us say there is a point charge which is kept over here, which is also plus Q. Then field at P produced will be identical and it is going to be KQ by r square. So field outside a spherical shell, field at a point which is lying outside the spherical shell is similar to that of a point charge kept at its center. So agar hum dono formula dekhte hain, then basically we have the inner electric field inside any point, the spherical shell is basically 0 and outside it is same as the point charge. If we make the graph, then here I am making a graph of electric field versus the distance from the center. So this is the distance from the center. So this distance is basically 0 to r, means we are going to talk about electric field inside the spherical shell, which is going to be 0. So it is 0 till from this 0 to r, and as soon as it comes to be r, it is KQ by r square, which is proportional to 1 by r square. And at the surface boundary condition, put r is equal to capital R, so it is KQ by r square. So it is suddenly becomes KQ by r square, and then it gradually goes down towards 0 and it proportional to 1 by r square. So here E is 0 and here is E is proportional to 1 by r square. So graph looks something like that. Next case is electric field due to a solid sphere. So we have a solid sphere and that is conducting solid sphere. So this is a conducting solid sphere. Now what is the difference between a conducting solid sphere and a shell? None. Why? Because if you give any charge Q to this conducting sphere, then entire charge will go and lie over its surface only. So we know that on this surface, the charge is lying over surface only. So all the charge is just lying at the surface, and hence it will just behave as a spherical shell. So entire charge is lying over here. Again, if you go at a point you assume this point is Q and I want to find electric field at Q. So I assume a Gaussian surface of having a radius r, and when you write same thing, flux is equal to Q in by epsilon naught. Here again the charge lying inside the Gaussian surface is 0, hence E will be 0. So electric field at a point which is lying inside the conductor is always and always 0. So this is a property of the conductor, as well as we can prove this using Gaussian surface. If we have to get electric field for a point which is outside, again we can take a Gaussian surface, and here the radius of the Gaussian surface is same as the distance of point P from the center of the sphere. And again when we apply the same formula, the flux is equal to Q in by epsilon naught, then we say that Q in is nothing but total Q, epsilon naught is epsilon naught. What is the total flux? If E is the field, magnitude of field, and it is radially away, so E dot ds means E ds cos theta or E dA cos theta. So theta is going to be 0 and integration is going to be just E times the total area. So electric field times the total area is 4 pi r square, and again we get the same result. It is same as the point charge, so which is KQ by r square. So this is going to be electric field at a point which is outside the solid conductor sphere, which is same as the shell also. So this is the formula which we get. E is equal to KQ by r square for a point which is situated outside. Let us have a look at both the formulas. So inside a conductor, spherical conductor, the electric field is 0, And this is the property of conductor, as well as we can prove this using Gauss's theorem as well. And electric field outside is same as if there is a point charge which is kept at its center. So you make the entire sphere as a point charge, put it over here and find the electric field. So that will give the same effect as the entire sphere for a point which is lying outside the sphere. Let us make the graph. So graph is also identical with the shell. So electric field, this is inside, this is outside, this is R less than R, and this is R greater than R. So here the electric field is 0, and here electric field is proportional to 1 by R square. So we get the same graph as spherical shell. Now, conducting solid sphere behaves same as spherical shell. We have already discussed this. Next is a non-conducting uniformly charged solid sphere. Now again, first we are going to discuss the electric field, which for a point which is lying inside the solid sphere. But this is non-conducting uniformly charged. So here the charge capital Q not just lies over its surface, the Q is distributed throughout its volume. Because it is a non-conductor, the charge is going to be distributed throughout its volume. So I will say that again, if I have to find the electric field at this point Q, then I am going to take a Gaussian surface. Let us say that is E. When I apply the Gauss's theorem, that is total flux passing through that Gaussian surface which I just drew, is nothing but Q in by epsilon naught. So what is the flux? Flux is E times, if electric field is E in magnitude, then it is going to be radially away only, given that it is positively charged sphere, times 4 pi R square, and we know that cos theta will be cos 0, which is 1, so I am not writing that. And then what is Q in by epsilon naught? So here Q in, the charge is distributed over a volume. So I will say total charge over total volume, that is 4 by 3 pi R cube, is equal to the required charge divided by the volume of this charge where this charge is distributed, which is 4 by 3 pi small r cube. So 4 by 3 pi is gone, and we can say that this required charge is nothing but Q small r cube divided by capital R cube. So you can cancel this R square with R square from over here. 4 pi goes there, and we get E is equal to this Q R cube and 4 pi epsilon naught. And this 1 upon 4 pi epsilon naught is K. So we get KQR by R cube. And this is going to be formula for electric field, which is electric field for a point which is lying at R distance from the center, given that R is less than the radius. So this is the formula which we just did, that KQR by R cube for a point R is less than capital R. What about this? So if you do this Q, what is rho? Rho is the volume charge density, that is total charge upon total area. So if you write Q by, so just divide it with 4 by 3 pi R cube. So this is K, which is 1 upon 4 pi epsilon naught. This is Q R and R cube. What I am going to do is I am going to divide both the things, like I am going to multiply and divide with this, and 4 by 3 pi R cube. What is that? That is the volume. So total charge upon total volume is nothing but density, volume charge density, and R divided by 3 epsilon naught. So it can also be written as rho R by 3 epsilon naught. That is another way to represent the same thing. Either you can remember this or you can remember this. If you want to be faster, you can remember both the formulas. Sometimes this is utilized, sometimes that is useful. So if you have a look at for a point which is lying outside. So again I am going to draw a Gaussian surface which is passing through point P if I want to get the electric field at point P. So again, when we apply for a point which is situated at a distance which is greater or equal to its radius. So when I do that, again I am applying Gaussian theorem. So that's Gauss's law says that Q in like flux is equal to Q in by epsilon naught. And when I want to write flux, is this nothing but E into 4 pi R square? What is the charge which is inside? Inside it, inside this Gaussian surface, the entire charge of the sphere lies. So I will write the entire charge Q is inside, divide by epsilon naught. Again we get E is equal to KQ by R square. So again that is same as a point charge, if a point charge, you make the entire sphere as a point charge and put this charge over here, then you get the formula for electric field for a point which is lying outside our spherical charge, non-conducting solid sphere. So let us have a look at the formula. So this is same as kq by r square for r which is outside the r which is greater than capital R, or for a point which is lying outside. So these are our two formulas, and let us have a look at the graph. So for a point, this is kqr by r cube. So here if you see, for a point which is inside the charge, the electric field is directly proportional to r, right? See, kq by r cube is a constant, so electric field is directly proportional to r. And for a point which is outside, again it is proportional to 1 by r square. So we will say that it will increase, and if you put small r is equal to capital R in both of them, then first becomes kqr by r cube. So that is kq by r square, and this also becomes kq by r square. So both the values, so it rises then up to all the way up to kq by r square, and then it decreases to 0 when it tries to reaches like towards infinity. The field is going to be 0. Now next is electric field due to infinitely long cylindrical shell. So we have a cylindrical shell, and that is infinitely long both sides. I have to get the electric field at a point P which is either inside or outside. So first let us cover the case where r is less than the radius of the cylinder. So for that, what I am going to do is, I am going to assume this Gaussian surface. So my Gaussian surface is also a cylindrical surface, and if it is infinitely long, see this is our infinitely long cylinder, going both the ways, going all the ways up to infinity, and I am taking a Gaussian surface also as a cylinder, and let us say length of that Gaussian surface is L, and the radius is small r, and here the field is, let's say, E. So now again, if E is over here, so due to symmetry we will say electric field should be E over here. If we go slightly below, then at this point also E has to be same in magnitude, because since this is infinitely long, for an infinitely long, this point and this point behaves identical, because here also above half, like above this infinite cylinder is there, and below this also infinite cylinder is there. For this point also same situation is there. Above there also infinite cylinder is there, and below that also infinite cylinder is there. So if it is E over here, then it should be same as over here. So due to that, we can say that throughout this Gaussian cylinder, we have assumed our Gaussian surface to be a cylinder of radius small r. So throughout that, the electric field should be just E. So first I have explained that let us take a Gaussian surface of length L and radius small r. So I have to find field over here. So what is Gauss's law says? Sigma flux is equal to Q in by epsilon naught. How much is the charge lying in this Gaussian surface? Answer is 0. Because the entire charge, this is a infinitely long cylindrical shell, and entire charge is lying over the surface. Our cylindrical Gaussian surface is inside it. So there is no charge lying in this region. So there is no charge lying in this region, and hence we can say that Q in is 0. And if Q in is 0, then it will be what? E times area, because E is already perpendicular. Due to symmetry, we can say that E will be perpendicular to the surface, or that angle between E vector and small area vector is going to be 0 degree, because area vector is also perpendicular to the surface. So this is going to be cos 0. So E into total surface area, which is 2 pi r into L, and that is going to be give me Q in, which is 0 by epsilon naught, and that leaves me E is equal to 0. So electric field for a point which is lying inside a cylindrical shell, and that cylindrical shell is infinitely long in both the direction, is 0. So this is electric field inside a spherical shell for a point which is lying inside a spherical shell, infinitely long cylindrical shell, and field is going to be 0. Let us discuss the next case for a point, electric field for a point which is outside the cylindrical shell. Here also I am going to assume the Gaussian surface to be a cylindrical surface of length L. Now I will say that this is having L length. Let sigma be surface charge density of this cylinder, like charge density of this cylinder. Now I have to again apply Gauss's law. So flux is equal to Q in by epsilon naught. So what is the flux? Again E into the surface area of our Gaussian surface. So that is 2 pi r L is equal to charge which is lying inside. So whatever is the charge on this cylindrical shell is the charge which is inside, and charge is nothing but surface charge density sigma into area of this, which is nothing but 2 pi capital R is the radius of that cylindrical shell, into L divided by epsilon naught. So here 2 pi and L you can cancel out, and hence we can say E is equal to sigma R by epsilon naught small r. So this is our formula for electric field at a point which is lying outside the cylindrical shell. So let us have a look at both the formulas. So E out is sigma R by sigma capital R by epsilon naught small r. And now both the formulas are inside it is 0, outside it is this. Let us have a look at the graph. So inside it is 0, so it will be 0 from 0 to capital R. Whenever R is varying from 0 to all the way up to R, the E is 0. And then when R is varying from R to all the way up to infinity, our E is basically proportional to 1 by R. So hence it decreases like that. And what about the value at the surface? Put capital R over here. So we'll get sigma by epsilon naught. And put R over here, then it is 0. So here it is a discontinuous graph. And suddenly, as soon as we go out of the cylindrical shell, it suddenly becomes sigma by epsilon naught, which is this value. Let us discuss the electric field due to infinitely long, uniformly charged cylinder, and that is non-conducting. So this is a solid cylinder. Previously we had the cylindrical shell. So here, if we are going to again find for a point which is inside. So in a shell, this Q in was 0, but now the case would differ. So I am saying let us say this be R. So flux is equal to Q in by epsilon naught. And here the volume charge density is rho, like charge per unit volume is my rho, and cylinder extend all the way up to infinity in both the direction. So now I am going to write flux is nothing but E into, what is the area? Area is 2 pi RL, assuming that this length is L, is equal to charge inside. So that is volume charge density into volume. How much is the volume of this cylinder? So see, whatever is the volume of this cylinder, when I multiply this volume with rho, I will get the charge which is lying inside our Gaussian surface. So volume of that cylinder is pi r square into L divided by epsilon naught. So just cancel out pi and L, and we get E equals to rho r square. R is also cancelled. So rho r divided by 2 epsilon naught. Rho r L. L also get cancelled. So rho r by 2 epsilon naught, and this is the electric field inside for a point which is lying inside the solid cylinder, solid infinite long cylinder, and which is uniformly charged, having a volume charge density as rho at a distance small r from its axis. So final formula is rho r by 2 epsilon naught. Then the point which is outside. Again I am going to do the same thing. Assume this Gaussian surface and write the same thing. So length is L. The volume charge density is rho. So I will write flux is equal to Q in by epsilon naught. So flux is nothing but E into 2 pi r L. That is the area, right? Cos theta is basically cos 0 as usual, and Q in. So what is charge which is inside that? Charge which is inside that is nothing but volume charge density into volume. But which volume? I have to take this volume because charge is lying only in this much of volume. So I will say that it is pi capital R square into L divided by epsilon naught. So here pi and L is gone, and at the end result is E is equal to rho capital R square by 2r epsilon naught. So this is the electric field for a point which is lying at small r distance from the solid cylinder, from the axis of a solid cylinder, and having a radius capital R and volume charge density rho. So this is the formula which we got, rho r square by 2 epsilon naught small r for r which is greater or equal to capital R, like at a distance which is bigger than the radius of the solid cylinder. So let us have a look at the graph. So graph is nothing but, here it is proportional to r and here it is proportional to 1 by r. So initially we will get a straight line rising proportional to r, and then we will get proportional to 1 by r, and at the boundary condition, that is when r is equal to r, put the value. So this is rho r by 2 epsilon naught, while this thing is rho capital R square by 2 epsilon naught capital R. 1 r is gone, and again we get the same thing. So graph is continuous at the boundary, that is small r is equal to capital R.